We're going to discuss higher order differential equations, in particular homogeneous linear differential equations with constant coefficients. Higher order linear equations are vital to the study of classical areas in mathematical physics, such as fluid mechanics, heat conduction, and wave motion. So at the end of this module, we will discuss some applications of these types of differential equations, in particular to spring problems, electrical circuits, which involve solution of second order non-homogeneous differential equations. Any equation that can be written in the following form is a non-homogeneous linear equation, where an minus 1, a sub 1 up to a sub o are either constants or functions of x, and then r of x is any function of x. If r is equal to 0, then the equation is said to be homogeneous equation. Let us consider homogeneous solution to homogeneous linear equations with constant coefficients. Okay, so the right hand side is equal to 0. The general solution is obtained by this equation, y is equal to y sub c plus y sub p. So the first type of solution is, or the first part is called the complementary solution, which is based on the derivatives, and then y sub p is called the particular solution, which is based on the right hand side of the equation r of x. But since we have a homogeneous linear equation, this time your r of x is equal to 0, and then y sub p will be 0 in that case, and then your solution or general solution will be based only on the complementary solution. Okay, so the derivatives can be expressed in terms of the operators. So for example, d raised to n is just d raised to n over dx raised to n without the dependent variable y, no? You get the d operator. So d is just d over dx. So using the d operators, okay, this is the original equation. You can factor out y here. Okay, factor out y. Okay, so that gives you the coefficients and the d operator. So we can rewrite this as follows, which can be considered as a function of the d operator. Okay, f of dy equals 0. And for every f of dy equals 0, there corresponds an auxiliary equation, no? Which is obtained by replacing d by m, and then getting rid the variable y. And then we solve for the equation, and then if m is a root, okay, of the equation that corresponds to a linearly independent solution in exponential form, so the arbitrary constant c, e raised to the root multiplied by x. So for distinct real auxiliary roots, so if m1, m2 up to mn are roots of the auxiliary equation, then the solution to the nth order equation f of dy, so there should be y here, equals 0, is given by this equation. So So every root corresponds to an exponential function and an arbitrary constant. So the number of arbitrary constants should be equal to the order, no, of the differential equation. Okay, so let's consider the first example. You have d cubed minus 4d squared plus d plus 6 equals 0. So this is the d operator. Okay, and then getting rid of y and then replacing d by m cubed minus 4m plus 6 equals 0. So this is a cubic, and if you want to solve for the roots of the equation, you may consider all factors of 6. So let's say, so I'll just solve one here. Okay, so let's take negative 1, that is one of the factors of 6, no? So, and then we write down the coefficient. So they are missing power. Put a 0 coefficient. This one is m squared. Okay. So bring down the first coefficient, multiply by negative 1. Okay, you get negative 1 here, you get negative, okay, you get negative 5. Okay, that's positive 5. And then 6, negative 6, so you get 0 here. So this corresponds to m squared minus 5m plus 6, which is factorable. So 3 and 2 both are negative. Okay, so the roots are negative 1, 2, and 3. Okay, and for negative 1, you have c1 e to the negative x, and then for 2, c2 e to the negative e to the 2x, and then for the root 3, you have c3 e to the 3x. So the order of the terms, no, or your roots, it's not really that important, no? Let us consider those that are repeated roots, no? So if m is a root repeated k times, okay, the solution will be of the following form. So y is equal to c1 c2x and so on, and then e to the mx. So take note, if you have k here, the power of x is always less than 1, no? And then if you have k times here, you have k number of arbitrary constants. So let's try that here. Okay, so this one is the factor out first y. Okay, and then this one is d to the 4th negative 7d cubed. Okay, 18d squared minus 20d, and then the constant 8. So the auxiliary equation again is obtained by replacing d by m and then getting rid of y here. And this is for fourth degree. No, you can try synthetic division, and then by trial and error choose possible values, possible values of 8, or rather factors of 8. So, and then you may try one, and then it turned out that the other roots are multiple of 2. So in this case, for 1, the solution is c1 e to the x, and then your k here, or 2, has a multiplicity of 3, no? So the form of solution would be c2 c3x plus c4x squared. So 3 constants, and then 3, k equals 3, so the maximum power of x is 2, and then times the exponential e to the 2x. What if we have complex roots? So if a plus or minus bi are complex roots of f of m equals 0, then the corresponding solution would be as follows. So this is the real part, and then this is the imaginary part. So you have 2 constants because these 2 are conjugates, to considered as two roots. Okay. Now if a plus bi is repeated 3 times, okay, so this is equivalent to 2 roots tapos repeated 3 times, so that's equivalent to 6 roots. So we expect, in case, c1 up to c6 3 times, so you have x squared, and then cosine bx, sine bx, then quantity raised to e to the ax. So take note, if you have pure imaginary roots, no, like say 3i here, and then let's say repeated twice, then your solution will be, so in this case your a is equal to 0, so no exponential, and then b is 3. Then you have 2 here, so 4 arbitrary constants, so c1 plus c2x. Okay. And then the cosine function, so cosine 3x. And then another polynomial here, so c3 is now c3 plus c4x, and then the sine function. Okay. Okay, so let's try solving example number 3. So this is already in the operators. Your auxiliary equation is m cubed minus 3m squared plus 9m plus 13. And then solving for the roots will give you 1 real root and then 2 complex roots, no? So in this case, if you have 2 plus 3i, then we'll take a equals 2 and then b equals 3. So for negative 1, that corresponds to the solution c1 e to the negative x. This will give you cosine, sine function. So c2 cosine 3x plus c3 sine 3x, quantity e raised to 2x. Now you can, in some cases you need to expand. Okay, so this is cosine 3x. Should, and then e to the 2x. So I should put the exponential here. Then c3 e to the 2x sine 3x. And then this one will lead to repeated complex roots, no? So this is 7th order. Okay, you can factor out m cubed here. This one is a perfect trinomial square whose factors are square of m squared plus 5, no? You can check. So square of this is m to the 4th. Square of 5 is 25. Then twice the product will leave you 10m squared. M cubed, so the root is 0 but with a multiplicity of 3. Now, the power 2 here indicates that this root has a multiplicity of 2. So take note that this, if you try to solve for m, that gives you negative 5m squared, then get the square root, will give you plus or minus the square root of 5 times the imaginary unit. So your a here is 0, and then b is the square root of 5 with multiplicity of 2. So for 0, no exponential function. If m is equal to 0, e to the 0 will give you, okay, e to the 0 will give you 1, okay, here. So if you have m equals 0, you only get polynomials, no? c1 plus xc2 plus x squared c3. So up to x squared only because it has multiplicity of 3. And then the same is true with the complex roots. So if a is equal to 0, so e to the 0x will be 1. So no more exponential here. But this one is repeated twice, so you have constant times x for cosine. Okay, the same is true with the sine function. Okay, so this is your general solution. Okay, let's consider an initial value problem. So how do we solve an initial value problem? So if this is third order, then we expect three initial conditions, no, for y, first derivative and second derivative. So meaning here the initial condition is when x is equal to 0, no? The value of y is 1, the value of y prime is negative 2, the value of y double prime is 2. Okay, so solving for this cubic differential, or rather third order differential equation, the root is negative 2 with a multiplicity of 3. So applying our formula, no, for the solutions, so this will give you c1 plus c2x plus c3 x squared quantity e to the negative 2x. But in this case we need to expand. Okay, so that gives you c1 e to the negative 2x, c2x e to the negative 2x plus c3 x squared e to the negative 2x. Okay, now we can now apply the first initial condition, no? So e to the 0 will be 1, y is sorry, this is 1. Okay, this should be 1. Okay, so this is equal to 1, and then c1 plus c2, x is equal to 0, so this will be 0, and that gives you c1 equals 1. Okay, and then get the first derivative. Okay, get the first derivative. This is negative 2 c1 e to the negative 2x. This is product rule. This is also product rule. Okay, and then apply the second condition that when x is equal to 0, the first derivative is negative 2. So you have negative 2 here, negative 2 c1. So all terms with x equals 0 will be 0. So this one is 0, 0, 0. c2 e to the 0 is c2, but this is 1. c1 is 1. Transpose, that gives you positive 2, so c2 is equal to 0. Okay. Differentiate again. So derivative of this is 4 c1 e to the negative 2x. Product rule. Okay. This one is negative this is combined with negative negative 2e to the negative 2x. That's why you get here negative 4. And then derivative of this by product rule. This is also by product rule. Okay, these two terms. And then apply the initial condition when x is equal to 0, y double prime is equal to 2. So this is equal to 2, then all terms with x will be 0. So this is 0, this is 0, this is 0. So you get negative 4c1, this is 0 also. Negative 4c2, and then 2c3. Okay. C1 is 1 here. And then C2 is 0, so this is 0. And C3, so negative 4 plus 2 is negative 2 divided by 2, that gives you C, negative 1. And then we substitute in the general equation here. C1 is 1. C2 is 0, so everything here will be 0. C3 is negative 1, so I get negative 1x squared e to the negative 2x. So this is our particular solution.